This is the second part of our discussion of Chapter 2, Section 2 from Calculus. We're talking about limits going to infinity and limits as x goes to infinity. What we're going to look at in this case is limits of functions as x goes to infinity. And this time the functions are not going to approach a number, but we'll see if there is at least something that we can say about what those functions do as x goes to infinity. So the first thing I'd like to do is compare the function 7x to the fifth minus 4x cubed plus 2x minus 9 to the function 7x to the fifth. I'm going to compare those visually on a graphing calculator, and I've set my window to -4 to 4 for the x's, -10 to 10 for the y's. This should give us a view of what these functions look like near zero. First, you'll see the longer polynomial being graphed. It'll come along in blue. And then you'll see the function 7x to the fifth graphed. It's going to come along in red. If we take a look at these functions, we can see they look fairly different near zero. But now I'm going to change my window. I'm going to change the x min and x max to -50 and 50. I'm going to change the y min, y max to -70 million and +70 million. And let's take a look at the graphs now. Again, first we'll see the blue graph. This is the longer polynomial. And now we'll see the red graph, which is just 7x to the fifth. And we can see from this perspective, these graphs look nearly identical. So what we're seeing is that far away from zero, if I make my x's fairly large, I'm getting nearly identical values for these two functions. Let's now switch to another pair of functions to compare. I want to compare the rational function 7x to the fifth minus 4x cubed plus 2x minus 9 all over 2x cubed plus 5x squared. Compare that to the rational function 7x squared over 2. So firstly, I'll change the window and look at what these look like near zero. X is -4 to 4. For the y's, -50 to 50. And as we take a look at the graphs, you'll see in black that that big rational function takes some interesting turns there, and as x gets a little bit larger, heads off towards infinity. Now we'll see 7x squared over 2. And it'll follow what we expect from a quadratic, just a simple parabola. So that's near zero. They don't look very much the same. These are pretty different functions. Let's change our window. I'm going to change x min, x max to -50 to 50. And y min, y max -10,000 to 10,000. Now let's compare those graphs. This is that large rational function. It seems to have just a little variation there near zero, but otherwise this is a pretty familiar shape. Compared to 7x squared over 2, these functions are looking much the same. at least for larger values of x, they look the same. Something different happens near 0, but we're going to concern ourselves with large values for x. This brings up the idea of an end behavior model. So if we consider the two functions that we started with, the long polynomial function 7x to the fifth minus 4x cubed plus 2x minus 9, and the polynomial function 7x to the fifth, we notice that neither one of these has a numerical limit. 7x to the fifth minus 4x cubed plus 2x minus 9 doesn't go to a certain number as x goes to infinity, neither does 7x to the fifth. But compare the two. This time not comparing visually, but comparing algebraically with division. In other words, the limit of the polynomial function over 7x to the fifth. We could determine this limit by taking a look at individual fractions, 7x to the fifth over 7x to the fifth, minus 4x cubed over 7x to the fifth, plus 2x over 7x to the fifth, minus 9 over 7x to the fifth. Reduced, those fractions look like this. The limit of 1 as x goes to infinity is 1. The limit of negative 4 over 7x squared as x goes to infinity, that just goes to 0. The remaining two fractions, if x goes to infinity, they also go to 0. So we wind up with a limit of 1 minus 0 plus 0 minus 0, or just a limit of 1. What this is saying is that for large x's, whether they be positive or negative, as x gets very large, the functions are virtually identical. Comparing them with division produces nearly the same thing over itself. That's why we got a 1 for that limit. The definition of an end behavior model is as follows. The function g is a right end behavior model of f, if and only if limit as x goes to infinity of f of x over g of x equals 1. You can have a left end behavior model if and only if the limit as x approaches negative infinity of f of x over g of x equals 1. Sometimes we can use the same function as a right end behavior model and a left end behavior model. In other cases, we may use one function for the right end behavior and a different function for the left end behavior. If we can use the same function for both the right and left end behavior, then we say that is an end behavior model. So if the ratio of the two functions goes to 1 as x goes to infinity, it means the functions basically do the same thing for the very far right or the very far left. So there are a few functions where finding the end behavior is very easy. For polynomials, we can find the end behavior model by simply taking the leading term. That is the term with the highest power. For rational functions, let's examine how we can find the end behavior for a rational function. And to do this, let's go back a little bit to our previous two functions. Recall that we were comparing seven x to the fifth minus 4x cubed plus 2x minus 9 over 2x cubed plus 5x squared. We compared it to 7x squared over 2. So where did I come up with that function to compare things to? Well, the simple answer is I looked at the leading term in the numerator and the leading term in the denominator. 7x to the fifth and 2x cubed. If I reduce 7x to the fifth over 2x cubed, guess what I get? 7x squared over 2. So for rational functions, to find that end behavior model, we simply look at the ratio of the leading coefficients. We reduce that, and that's the end behavior model. Remember, when we looked at these graphs on a large window, we saw identical behavior or nearly identical behavior to the right and to the left. This means for a rational function, the end behavior model is always the ratio of the leading terms. If we want to see these written out in detail, this is a representation of the limit of any polynomial function as x goes to positive or negative infinity, and we simply use a term that's identical to the leading term. For these rational functions, a polynomial divided by a polynomial, we take the limit as x goes to positive or negative infinity, we'll simply use the ratio of the leading terms. So this a sub n x to the n over b sub k x to the k. The ratio of those leading terms, the ones with the highest power. So some textbooks will call them end behavior models. That's what our textbook does. Other textbooks will simply say that the limit as x goes to infinity is this function, or the limit as x goes to infinity is this ratio function. To see some examples of non-polynomials or non-rational functions and determine what their end behaviors are, I'd refer you to example 7 on page 70. And for practice with end behavior models, I'd like you to try page 76, 35 through 38, 39 through 51 odd, and number 58. Just a few other hints and reminders. To find a horizontal asymptote of a function, identify the horizontal asymptotes of the end behavior models. They will be the same thing. If you want to find the limit of a function as x goes to infinity, we could look at the limit as the f of the reciprocal goes to 0. As an example, if we wanted to know the limit as x goes to infinity of f of x, we could look at what happens to f of 1 over x as x goes to 0. Graphing f of 1 over x essentially turns f of x inside out. All the things that happen to f of x on the far edges of the graph will happen to f of 1 over x right near the center of the graph at x equals 0. See the book for more examples of these things. Thank you for watching this. I'll see you in class.